Let's talk about the numbers we use every day. You might think they're simple, but they're governed by these surprisingly elegant and powerful rules. And we're going to unlock some of those secrets right now.
All right, here's what's on the docket. We're going to start with this really cool ancient puzzle about bees, of all things. Then we'll see how that puzzle actually reveals a super powerful mathematical tool. From there, we'll crack the secret code of numbers, and then, just when you think you've got it all figured out, we'll meet the numbers that seem to break all the rules.
Okay, first up, a puzzle. This is where we see that math isn't just some dry formula in a textbook. It's a really creative way to solve problems.
So you might be thinking, why are we starting with an ancient puzzle? Well, this isn't just some random brain teaser. It's actually a gateway, a way to understand a really fundamental concept about how numbers relate to each other. All right, so get this. Here's the puzzle. You've got a swarm of bees, and you know there are 50 at most. If you group them in twos, there's 1 bee left over. Group them in threes, 2 are left. In fours, 3 are left. But if you group them in fives, there are none left over. It's like a set of clues, right? Our job is to be the math detective and figure out the one number that fits all of them.
So how do we even start? Well, a good strategy is to work backwards from the clues we're given. The easiest one is that when you group by 5, there are none left. That means the number of bees has to be a multiple of 5. The next clue? When you divide by 2, there's a remainder of 1, which is just a fancy way of saying the number is odd. So right off the bat, we've taken all the numbers under 50 and narrowed them down to just these 5.
Okay, so now we just test that shortlist against the last couple of clues. And when we do, only one number works. 35. Check it out. 35 divided by 3 is 11 with a remainder of 2. Yep, that works. 35 divided by 4 is 8 with a remainder of 3. That one works too. It's the perfect fit. This little puzzle is a great example of how you can use systematic division to slice right through a problem.
And here's the really crucial point. That whole process we just used, division and remainders, it's not just a trick for bee puzzles. It is an incredibly powerful mathematical tool that was formalized thousands of years ago.
This is the formal rule behind what we just did. It's called Euclid's division algorithm. And yeah, it looks a little scary with all the letters, but all it's really saying is that for any two positive whole numbers, you can divide one by the other, and you'll get a clean answer, that's the Q for quotient, plus some leftover bit, the remainder R. It's a super foundational idea that basically organizes the entire world of integers. To make this a bit more real, let's forget the bees for a second. Imagine you have 2 strips of paper. One is 100 centimeters long, and the other is 60. Using this algorithm is kind of like finding the biggest possible chunk you could cut that would perfectly measure both strips with absolutely no paper left over. We're looking for what's called their highest common factor, or HCF. And here's how that algorithm looks in action. It's actually a really beautiful repeating process. Watch this. First, you take 100 and divide it by 60. You get 1 with a remainder of 40. Now here's the magic trick. That remainder, 40, becomes our new divisor. So next step, we divide 60 by 40. We get 1 again, but this time with a remainder of 20. We do it one last time. The new remainder, 20, becomes the new divisor. We divide 40 by 20, and what do we get? A remainder of 0. And the moment you hit 0, you stop. You found your answer. It's the last remainder you got that wasn't 0. In this case, it's 20. Okay, so from division, let's shift gears a little and see how this builds. Now we're going to look at the atoms of multiplication, prime numbers. This right here, this is one of the absolute cornerstones of all math. It's called the fundamental theorem of arithmetic. And it basically says that every whole number bigger than 1 is either a prime number itself, or it can be built by multiplying prime numbers together. And this is the really important part. For any given number, there's only one unique set of prime numbers that will build it. It's a one-of-a-kind recipe. You can think of it like a unique DNA sequence, or maybe a fingerprint for every single number. So take a big number, like 27,300. Its prime code is 2 2s, 1 3, 2 5s, a 7, and a 13, all multiplied together. No other combination of primes in the entire universe will get you to 27,300. It's a totally unique signature. So, okay, we've got this beautiful, orderly system, right? We have whole numbers, and they're all built from these prime number building blocks. It all seems so perfect. But what happens when we find a number that just doesn't fit? A number that breaks the rules?
This simple question, can every number be written as a simple fraction? This led ancient mathematicians, probably the followers of Pythagoras, to a discovery that must have been absolutely shocking to them. It was like finding a glitch in the matrix of their perfectly logical world of numbers.
All right, to figure this out, we're going to use this brilliant kind of mind-bending technique called proof by contradiction. Here's the game plan. We're going to assume the exact opposite of what we're trying to prove, and then we'll follow that assumption logically until it leads us to a complete paradox, something impossible. So let's start by pretending that the square root of 2 can be written as a simple fraction, a over b. And we have to add one really important rule. This fraction is in its simplest form. That means a and b don't share any common factors.
Okay, so if we start with our assumption that root 2 equals a over b, we can just do a little bit of simple algebra. Let's square both sides of the equation. That gets rid of that pesky square root, and it leaves us with 2 equals a squared over b squared. If we just rearrange that a little, we get 2 times b squared equals a squared. Now, this is a huge first step. Why? Because it tells us something really important about a squared. It has to be an even number, right? Because it's equal to 2 times something.
Okay, now think about this for a second. It's a fundamental property of numbers. If you square an even number, you get an even number. If you square an odd number, you get an odd number, right? 3 times 3 is 9, odd. 4 times 4 is 16, even. So if we know that a squared is an even number, we can say with 100% certainty that the number a itself must also be even.
And this is where the trap springs. Since we know for sure that a is an even number, we can describe it in a different way. We can say a is just 2 times some other whole number, let's call it c. Now, we take this new way of writing a and plug it back into our equation from before. After we do a little bit of simplifying, we find that b squared is equal to 2 times c squared. Wait a minute. That looks really familiar, doesn't it? It means that b squared is also an even number. And if b squared is even, well, b has to be even too.
And there it is, the contradiction. The whole thing just collapsed. We've logically proven that a must be even and that b must also be even. But hang on, go all the way back to the beginning. What was our first rule? We assumed that the fraction a over b was in its simplest form, with no common factors. But if both numbers are even, they obviously share a common factor of 2. Our starting assumption has led to an impossible conclusion. It can't be true.
So what does that mean? It means our initial assumption has to be wrong. It's just false. The square root of 2 simply cannot be written as a neat little fraction. It breaks the rules. And this discovery forces us to admit that there's a whole new, kind of mysterious class of numbers out there, the irrationals.
So this is really the big takeaway here. The real numbers that we use every single day are actually split into 2 very, very different families. On one side, you've got the rational numbers. They're neat, they're predictable, you can always write them as a fraction, their decimals either just stop or they fall into a nice repeating pattern forever. But on the other side, you have the irrationals. These are the wild ones, numbers like pi and the square root of 2, whose decimals go on and on and on to infinity without ever repeating a pattern. They're untamable.
You know, we started with a simple puzzle about b's, and we ended up at the edge of infinity, discovering numbers that break all the rules. It just goes to show you that math is full of surprises. It's a reminder that even in the things we think are most basic, there are always deeper structures, more secrets waiting to be explored.